Okay, so last unit of the class here, we'll be talking about dynamics of rigid bodies still, but now in full 3D motion. Okay, so let's start with, well, name of the class, right? As we start our last unit here, remind ourselves this means we'll be studying, and it'll be in this order, right? We need to revisit kinematics first, description of motion, independent of the forces that are causing or changing that motion, and then kinetics that follows. Okay, so we basically have two main units left. Couple lectures here on kinematics, and then we'll end with a few lectures on kinetics. Okay, we'll only be analyzing just the direct force, mass, acceleration equations of motion. All right, we won't be analyzing work energy here or the momentum relationships. I don't know of a better word to put over here, but just to call it an ugly moment equation in general here. So as we go into full 3 dimensions, things get a bit ugly. But if we just trust the math, set it up, do our problems in a methodical way, right? Take a methodical approach. We can, guarantee success here. Now, kinematics, I'll just, much of what we've done, we've left purposely general, at least in terms of like we derived an equation or we represented an equation, and it starts out general. And so that means it works for 3-dimensional motion. So much of what we've done is general for 3D. We just need to go, back to that analysis and say, hey, where did we leave the 3D generality, and plug in planar motion, and we'll have to start from there. Okay, it will have to definitely start more general here than other results that we've we've been utilizing here. Okay, now the 3D term here, right? So what we mean by 3D motion as opposed to planar motion, let's just take an example. It just means that there is now motion in all 3 dimensions. So as an example, for example, just the rotation axis changing in time. And one way that can happen is if you have something spinning that's also rotating about another axis. So if you have, a spinning disc that then is turning. So maybe you're riding your bike and your front wheel is going around and around, and you start to make a turn. That's going to turn. And that's true 3-dimensional motion, right? As your wheel, we're kind of looking down at the top of a biker, right? Biking forward, and as we turn our wheel, that's going to be and kind of lean also into it. There's going to be many different dimensions in which the dynamics are occurring. I mean, all 3 of them. So we have our rotation axis changing in time, such as or like turning a bike's handlebars. The wheels are in 3D motion. Wheels is motion. Is that okay? I think it's okay. Is 3-dimensional. We're using all of the dimensions. Now, if we were just riding straight ahead, that's planar motion. Riding straight ahead, the wheels motion is 2D, and we called that planar. And we'll actually give a mathematical description, but I just want to give, before we jump into it, an example here, right? Just something that is more intuitive, hopefully. Okay, so let's get into now the more technical description, right? So before we really dive in, we're going to get to the kinematics of 3D motion. To get there, let's describe what we've been studying and then relate this to what is coming. Okay, so in planar motion, if we remember, so the whole idea was that the motion, the velocities of points on a rigid body, were described in terms of their velocity and acceleration. Okay, these in general had 2 components for planar motion, meaning that the motion was all on a plane of a rigid body, at least with respect to one another, or if we went into the reference frame of that rotation. And this all stems out of the fact that we could put a rotation, so angular rotation and angular acceleration and angular velocity, those had 1 component. Okay, There was only one plane in which there could be rotation for this, rigid body. And also, we only had to calculate one moment of inertia. So an I value here, which was in a moment of inertia, has one component. Okay, so where things get tricky, just like logistically in terms of the number of components we have for all these things, now we have to consider that our motion for any point we look at could have all three dimensions, so it has three components, and this is because our angular dynamical properties like acceleration and velocity have three components, right? So the rotation could be in all three dimensions, and our properties here, which is a moment of inertia, but we're also going to add this thing called a product of inertia as we go along. They actually have 6 components. We're going to have 6 different of these geometrical properties for a shape. So things are getting, ugly. Things are getting messy. But if we take this step by step, hopefully we'll develop a method that then we can apply, right? We're going to trust our procedure, trust our method, trust the math. Okay, first, the whole goal of today, of this lecture, is to focus on a kinematic description of 3D motion. Okay, so we'll start with the general description of 2 points and how their motion relates on a rigid body. Because we have dealt with this in the past, and we're not going to have anything different. Okay, so let me put in a reference frame, and this will be our primary reference frame. Okay, it's the one that usually we choose this to be like affixed to the ground. And now let's put a general body up here, some rigid body, something that we can hopefully find, we can describe here. Oh, and we don't need to visualize as 3D, but it's definitely a 3D object that we're trying to represent. This we'll call the body. And right, so it has that like little curly B looking thing, and actually if I did the primary the right way, would be careful and put a P, kind of more script version, and that's just so we can use those subscripts. Okay, so I'm going to try to be really careful with my coloring here, at least at the start as we work through this. Let's say we got 2 points on here, A and B, and and then let's also say that there's some point in here. And it's actually, you can refer to this many different points, but let's just say there's some axis about which the body is rotating. Okay, so there's an omega for the body, right? And that's by definition, the way we're writing it here is in terms of the primary reference frame. Okay, and so that means, right, that's your thumb, and then the rotation of the body is about that axis. So it'd be something like, right, the actual motion would be like that, or maybe, right, the whole body is kind of rotating about that axis, right? Okay, so this is what I mean by the colors. If we write out the velocity here, the subscripts, hopefully I'll try to maintain a color. Okay, so we want to represent the velocity of, and I chose red for my points, so for point B is going to be the velocity of point A plus the rotation of the body, so there's a different B, this is the script B, crossed into the relative position of B with respect to A. Okay, see how we've done that? Now let's describe all these. We're going to take it really nice and slow here so we don't get into the last lecture of the class, which is many lectures away still. And we're confused with this notation, right? So remember, when we write this, anything with just like a subscript here, what we're referring to is an absolute quantity, and so this is probably the last time I write absolute, but the meaning in terms of primary, right? This is the absolute velocity of B, and we'll include A here too, B and A, with respect to the primary, or the O, reference frame. Okay. All right, so that's good. So those are both absolute velocities, and they are related through this. Well, let's put the relative position one in there first. That one's not. We've had practice with this one, right? So this is the relative position of B from A Okay, and then this guy here is our angular velocity of the body with respect to the primary. Okay, so that's O, the primary reference frame. All right. Okay, so we've seen this relationship before, but just getting comfortable with the subscripts. And remember, this is actually this whole second term is the relative velocity of B with respect to A. Okay, it's another way to think about it, right? So it's like to go from the velocity vector at B, you could either, to represent it, you could say, well, that's the velocity vector at A, and then the relative velocity of B with respect to where A is pointing, or where A is what A's velocity is. All right, now let's do something similar for the acceleration, and again, this is nothing new. We've seen this before. Okay, so I want to represent the the absolute acceleration at point B to the angular. Oh gosh, I said it again. There's too many A's. To the absolute acceleration with respect to the primary reference frame for A, and that's going to have a few different terms. So I'm going to jump forward. I'll put the subscripts in afterward. Crossed into an omega, crossed into an R. Okay, leaving space for those subscripts. Okay, so this is now the acceleration, or the angular acceleration of the body. This is a relative position B with respect to A. We got the angular velocity of the body crossed into the cross product of the angular velocity of the body with this relative position vector. Okay, so the only thing new here that we've added is this term. This is our angular acceleration of the body with respect to the primary reference frame, and we label that primary reference frame as the one with that origin O. Try to, usually try to keep that fixed. Okay. Okay, great. So really nothing new. That's good. But we are gonna do something new here, which is to extend this for multiple reference frame. All right. So in order to describe bodies rotating about another body, like that thing we talked about with the wheel rotating this way, and then it starts to rotate itself. Right, as you turn, right, your wheel's going around and around, and then it looks like almost like the rotating wheel is rotating about this fixed point as you turn a corner. Right, so in order to rotate something that's rotating about another point, right, at some distance away here, right, we're going to need to kind of not just have this body, but we're going to have a reference frame in between as the thing that is rotating. Okay, so what we're gonna do is come in here. Well, let's first, let's first give this a title, and then we'll actually add something to our figure back on this previous page. So what we're doing here is we are extending, and we don't need to change anything there, right? Those are all done, but we need to specify what we mean by how the body is rotating. So we need to extend for multiple reference frames. Okay, and this allows us to describe bodies rotating about, other bodies, about another body, about another point, about another reference frame. Well, I don't know, we want to keep this general, right? So it's bodies rotating about bodies, right? Or bodies rotating in these secondary reference frames. Okay, so that's going to look like this, okay? So I'll just write it down first, and then we'll add something to the picture. What we mean when we say the angular velocity of the body, sometimes it's going to be convenient to relate this to the angular velocity of the body with respect to a secondary, so that's going to be in purple, secondary reference frame, plus the rotation plus the angular velocity of this secondary reference frame. So the picture all we need to do to modify the picture here is add, well, maybe there's a reason to have a secondary reference frame. Oh, this is purple. And maybe it's rotating, so at the current state it's kind of at this angled. So this is our secondary reference frame that's rotating. And maybe currently, right, this is the coordinates. And the reason we have the secondary one is it's convenient for the coordinates. We express things in terms of this coordinate. Okay, so we're like at all of these positions, we'd like to be able to represent them. This rotation, we'd like to represent it in terms of this rotating coordinate system, right? Useful coordinates. All right, so it's this link in between. Okay, it's a secondary, and then we have three different reference frames, right? The body that's rotating, it's rotating with respect to this reference frame. Well, that's easy to do, but this thing itself is rotating with respect to the primary reference frame. Okay, so let's, we already talked about this one. This is that rotation of the body with respect to the primary. Well, that can then be written in terms of the, well, that's still just a subscript s here, so this is that, very similar definition, which is the angular velocity, so a rotation rate of the secondary reference frame with respect to the primary, or the O reference frame. Okay, and I want to note one thing here is actually throughout this entire chapter, I think the book keeps things a little bit too general, perhaps from what we actually are going to use it, and uses a notation that I think is unnecessarily extra complicated than it needs to be. Not that anything here should, this is going to feel very complicated already. But to me, I thought denoting this with this other rotation vector didn't make sense. We could just do it with the subscript here, right? So they denote this as this capital omega, right? And I get it, that's a capital, Greek letter, that's a lowercase Greek letter. But to me, let's just subscript it with something else and have the S there for stand for secondary, okay? And then this thing right here is also new. This is now the angular velocity of the body, so in blue, with respect to the secondary, and that is the S reference frame. Okay, and now this again, right? Oftentimes, like we're doing this because this is like what is more natural, right? This is like the secondary is sitting there rotating with the reference frame, and this quantity comes naturally. It's usually specified in the problem statement, right? And so is this, right? So we've got this relative angular velocity that's usually specified in the problem, and so this isn't hard. Like this, getting to this might not seem natural, and that's why we have an equation for it. So it really does usually flow in this direction. This is what's obvious in a problem statement. This is what's obvious in a problem statement. Add them together and you get this thing, right? Actually, well, make sure we're adding the vectors. Okay, so quick note here about notation. This is denoted relative angular velocity in the book. Again, the same reason that I said over here. I think it's easier this way, right? More consistent with the notation we've been using. Okay. Now, before we move on, we're going to move on to acceleration here, but let's just step back, and now we've seen the primary, we've seen the secondary, and we've seen the body. Let's just make sure we understand what all three of those are. So we've got a body, we've got a secondary, and we've got a primary. And what I'd just like to do here is take a minute to describe why we have these three, and the best we can do maybe motivate why we have three different things. And I think I've already done it a lot, right? But more just like descriptively, right? That's kind of like mechanistically here, like how things are done. But in more a philosophical approach, what we have here is a body. It's really some sort of object, some sort of element in our system that's rotating about another component. Okay, and I'll put these in quotes because there's really no good language for something that really is general in nature. So anytime I put something on there, it's going to feel like something more specific than it really is more general, right? Whereas this secondary is then some component that the body is rotating about. Okay, so that seems to be like a cyclic definition, and it should. I mean, it should kind of feel like we're defining one and the other. Now, this oftentimes could be, I say could be, well, the only reason we're talking about is it normally is, could be rotating in the primary reference frame, or with respect to, I should say, with respect to the primary reference frame. So maybe we'll, with respect to is what I mean when I say in. And then when we get to the primary, right, what is this? Well, this is usually grounded, right? So this is typically fixed to the ground and is often what the kind of answers we want. We want to know what the speed is, you know, the absolute speed of the bike as it's turning the corner, right? That's usually, because it's how questions are posed, right? Typically fixed to the ground with rotating. And so we choose this as the primary reference frame with rotating components and objects, however you want to define them. Okay. So we'll see this as we get to the examples. Before we do that, before we wrap up here in this video, we're going to do the same thing we have up here for angular velocity with angular acceleration. So to describe these bodies rotating about bodies, we need the angular acceleration of the body, which is something that's not so obvious from a problem statement in terms of things that are more normally given or natural to be given in a problem statement. Okay, kind of similar to like we had up here. We're going to have the angular acceleration of the secondary reference frame. We'll have an added term that is the relative angular acceleration of the body with respect to the secondary rotating reference frame there. And then we have a term that looks like this. It is a cross product of these two terms up here. Okay, so it's an omega s crossed into, and I'm being so careful as I'm talking here to get these colors right, body with respect to s. Because I don't know, I think it's a really nice visual. I hope it's coming through in the video you're watching. If it's not, then this is some wasted effort, but that's okay with me. I at least have a nice set of notes here. Okay. Angular acceleration of the secondary reference frame with respect to primary, where primary is O. Okay. That, we've seen that definition before for omega. Now we're just doing it with alpha, the angular acceleration, instead of angular velocity. We've seen this definition before when that was an omega, now it's an alpha. So this is angular acceleration of the body with respect to secondary. Oh, let's keep it here with respect to secondary. And so what we mean is S. And then these two things we've defined before, but why is it showing up as the cross product? Well, this accounts for effects of the rotating body. This then accounts for what. Okay, this is a result, and if this is non-zero, it's because the body is changing directions within that secondary reference frame. Okay, and that's these cross products, right? So if there's a relative difference in the rotations of the body with respect to that secondary reference frame, that causes an extra acceleration. Okay, rotating body, changing directions within secondary S. Okay, body B. Okay. Now, that's it. That's all of the theory. We're going to jump right into examples in the next video here. But I do want to just note one thing, right? What with this notation, what this means is if there is just a subscript and nothing else, that is with respect to the primary, right? The only way it's something with respect to secondary is if we explicitly say it here with this, like, with the relative notation, right? Okay, come back with a couple examples in the next video.